Alright, so in this video we go over section 5.5, applications of exponential functions. In this particular video we cover applications to elasticity of demand. The elasticity of demand function is a function that tell us whether revenue is increasing or decreasing. And well, this is an application more to economics and finance. And well, there is a formula to find that elasticity given a demand function. And well, that formula to find the elasticity function is right here is -1/x times the quotient between the demand function and its derivative. So that's all we do to calculate the elasticity function, and its properties are right here. So when E is a positive value, then the revenue is increasing, and we say that the demand is elastic in economical terms. Otherwise, if E is a number less than 1, then this revenue is decreasing and the demand is this should be inelastic. There's a little typo here. I will correct, but it should be corrected in the PDF file. And otherwise, when E is exactly equal to 1, then, well, the revenue is exactly at its maximum point, and we say that the demand, it has a unit elasticity. There's another little typo here as well that it's also fixed on the PDF file. So let's have a look at one example. So we were given a price function, which is the demand function. So you could be given these type of functions as either the price or demand. They recall from older sections from the beginning of the semester that it's the same thing. So they're giving us a function d of x equals 300 minus 2x. What is the price per unit if 5 units are sold? So in this case, well, all we have to do is evaluate, so to find the price, so P, which is d of x, d evaluated at 50, that's a 300 minus 2x, where x in this case is the 50 units. And using a calculator to simplify this, well, so this is 300 minus 100, which is 200. Well, in this case, you might want to, put units of dollars because we're talking about money, its price. Well, in this case, we're assuming it's dollars. Okay, so they're asking us to find the function describing the elasticity of demand E. Well, so to find the elasticity of demand function, we need to consider the elasticity function. We need the D function, which is, let's consider it again, 300 minus 2x. And we need to take the derivative of this function, which in this case is -2. And then we will find the elasticity of demand function, which is given by E equals -1/x times the quotient of the demand function to its derivative, d prime x. And this is going to be -1/x times d of x, which is 300 minus 2x, whole thing divided by the derivative, which is -2. And simplifying this to lowest terms, we're going to get the following. Okay, negative, notice this negative times a negative is going to make it a positive. So that's going to get, and multiplying across x times 2, that's going to give us 300 minus 2x divided by 2x. And in this case, we can simplify this a bit further because notice how the numbers 300 and 2 are both divisible by 2. So let's simplify that. So that's 150 minus x divided by x. So that's our elasticity function. All right. So let's have a look at part C of the problem. So for part C, they're asking us to find the elasticity when x equals 50 and the elasticity when x equals 110. All right, so let's plug this in. So again, let's recall what the elasticity function is. So E equals 150 minus x over x, and in this case, let me erase this part. So E of x, so E evaluated at 50, that's 150 minus 50 over, well, let me actually use a different color just so it stands out. So evaluate that at 50. So that's going to give us 100 in the numerator and 50 in the denominator. That's a 2, which is a number greater than 1. That means in this case the demand is elastic. And therefore revenue is increasing. On the other hand, let's have a look at what happens when x equals 110. So E evaluated at 110, that's 150 minus 110 divided by 110. And in this case, we get the following. So that's 40 over 110, which is approximately, in decimals, using a calculator, that's going to give us a 0.36. And in this case, this quantity happens to be less than 1, which means that the demand is inelastic. In this case, revenue is decreasing. All right. Now, in this case, we want to know, so we can plug in many values of x and play with this elasticity function and find out where the demand is elastic, or when the demand is inelastic, that means where our revenue is increasing and decreasing respectively. However, what we want to know, and you as a businessman, what you want to know is where is your revenue the maximum, because it's for whatever business that you're working at, that you're in charge of, well, you want to make sure that you make the most out of it. So in this case, what quantity makes x, what quantity x maximizes the revenue? Well, recall as well the revenue function from chapter, I believe it was chapter 2 or 3, where r of x, which is the revenue function, equals x times the demand function, which in this case is going to be x times this d of x, which is 300 minus 2x, which equals negative 2x squared plus 300x. All right, so how do we know where is this a maximum? Well, we need to take the derivative of the revenue function, which happens to be negative 4x plus 300. And we want to set this equal to 0 to find the values of x that make either a max or a minimum. Well, in this case, we're looking for the maximum. And also, I mean, you can tell that this is going to give us the maximum because you have a quadratic polynomial which models a parabola, and because of the negative leading coefficient, that's a parabola that opens down, which means that we will have a maximum. All right. So in this case, well, let's do this anyway via calculus, so that's a negative 4x plus 300 equals to 0. That means a negative 4x equals to negative 300, and then divide both sides by 4. That's going to give us 75. So if the price x is 75, or rather if x is the quantity is 75, then we have a revenue to be the maximum. And of course, you might want to use the second derivative test. Take r double prime, that's a negative 4. This means that the second derivative is equal to 0. And because the second derivative is equal to 0, this means r of x is concave down. And because area of sorry about that, because r of x is concave down, means that we have a maximum point. So different ways to verify test. The other way, it would be to make a table, use a test value, a number below 75, a number above 75, and do the change increasing and decreasing. But that's a lot more of work. In this case, it's simple to take the second derivative and really easy to look at the sign of the second derivative, which in this case is, well, it's a negative second derivative, which means concave down, the function attains a maximum at that point. All right. Let's look at another example. So a product is known to have a demand function of P equals d of x equals 100 e to the negative 0.5x. Find the value of x for which e is 1. So we're looking for the value of x for which the elasticity is equal to 1, which in this case it means that we have the maximum revenue. Coming back to the definition, so when e equals to 1, then the revenue is at its maximum, right? So that's essentially what we're doing, but we're doing this using the elasticity function, not the revenue function. So let's see. Let's find the value. Okay, so number one, we need to find also the derivative of the function, that is d prime of x, which is 100 e to the negative 0.5 x times the derivative of the exponential, which is negative 0.5 x. Oh no, not x, just a 0.5. Okay, so let's simplify this derivative. That's going to give us 100 times negative 0.5. That's negative 50 e to the negative 0.5 x. All right, so that's our derivative of the demand function. Let's set up the elasticity function. It's negative 1 over x times d of x over d prime of x. And in this case, well, so what do we have for d of x? That's 100. Oh, let's set up the other part as well. That's a negative 1 over x times 100 e to the negative 0.5x divided by negative 50 e to the negative 0.5x. What's going to happen here? Well, the exponentials go away, which is going to be a really, really nicer function. And this 100 over 50 will be a 2 over 1. Also, negative times a negative equals to positive, so that's going to give us the elasticity function E equals 2 over x. All right, so that's the elasticity function. E equals 2 over x. Now what we need to know is for which value of x is, okay, so find the value. So for which x is e equals to 1. Well, so we're going to do the following. We're going to plug in e equals to 1. That is e equals to 1. Plug it in here. So 1 equals 2 over x. And this equation is a really simple rational expression, a rational equation for which we can just do cross multiplication. And that's going to give us x equals to 2 units. All right. So selling or having x, the number of units, to 2 would give us an elasticity equal to 1, which would give us the maximum revenue over here. All right, so let's have a look at the next part of the problem. Now, find the value for x that maximizes the revenue. First of all, we need to set up the revenue function, which, by the way, is r of x, again from chapter 2 or 3, x times r of x. And in this case is x times 100 e to the negative 0.5 x, which reduces to, okay, let me rewrite this as 100 times x e to the negative 0.5 x. Well, so let's take the derivative of the function. So r of x equals, or rather r prime in this case. Notice that in this case we will have the product of the functions, a product between x and the exponential function. All right, so we're going to use the product rule along with the exponential rule to get the derivative of this function. And when you have a function like this, my advice is that you leave all coefficients, kind of leave them outside. What do I mean? So this 100 times whatever I get from taking the derivative of this product right here. All right, so I'm going to take this product individually and I'm going to write it down inside of the brackets. So the derivative, let's recall the derivative of a product. So whenever you have uv prime, that's a u prime v plus v prime u. In this case, consider x the u and the exponential r of v. All right, so that's going to be our u and v respectively. I don't know what happened here. All right, so let me erase this. Okay, I don't think we really need it. So the derivative of u, which is the derivative of x, the derivative of x is simply 1 times e to the negative 0.5 x, and then that times the derivative of the exponential, which is itself. Recall that the derivative of the exponential is itself, times the derivative of the exponential, but times x, which is the u part. So let's see, let's label this. So this is u prime v prime u. All right, so that's our product rule in action. Now let's see, equals 100 1 times e to the negative 0.5, that's e to the negative 0.5 x plus, or rather negative, minus 0.5 x e to the negative 0.5 x. So what I'm going to do here is distribute the 100, or you know what, see, we can simply do, okay, no, I think it would be better if we just, well, look, we can leave it like this. Actually, it would be better, no, yeah, let's distribute the 100. Let's distribute and multiply over here. It will be better actually. You'll see why. So this will be r prime of x. That's 100 e to the negative 0.5 x minus 100 times 0.5. That's half of 100, which is 50 x e to the negative 0.5 x. And notice in this case, yes, I know I distributed already the 100, but I'm going to factor out the exponential function. So that is e to the negative 0.5 x times 100 minus 50x. And in this case, well, again, what do we want to know? We want to know the value of x that maximizes the revenue. And in this case, we need to set this revenue equal to 0 and solve for x. Well, so let's see. So let's set up the derivative of the revenue e to the negative 0.5 x times 100 minus 50x equals to 0. On the one hand, we're going to have the following. By the zero product property, e to the negative 0.5 x equals to 0, or 100 minus 50x equals to 0. Notice in this case, the first equation, e to the negative 0.5 x equals to 0, that's not going to give us any information because in this case, the exponentials never go to 0, like in this case. However, over here, that's 100, subtract 100 from both sides, we get negative 50x equals to negative 100, and dividing both sides by negative 50, we get x equals to 2. Again, yes, it's the same result as what we got in part A. However, in part A, we did it using the elasticity function, using the fact that when the elasticity is 1, that means that we get the maximum revenue. The other way to get the maximum revenue is to get the revenue function and take the derivative of the revenue function, set it equal to 0, and solve for x. As you can tell, it was actually a little more work to do it using the revenue function. So in some cases, the elasticity function right here might be our best friend when it comes to finding this, because in this case, it gave us a way shorter way shorter process. All right, so this is the end of this video. So this is a good place to quit. I'll see you in the next video.